In this problem, we are going to evaluate the slope stability. And as you see, we have a railway cut with a specific attitude, and then the bedding attitude it's given, and we know the friction angle of the rock, which is 30 degrees. So this problem has two different ways to solve. I'm gonna do in both different way and explain you step by step. But before going through that, let me first to write down what kind of information I have. So the railway cut has a slope of 70 and is dipping towards 150. Indeed, the railway cut, right, it's a plane, right? It says this plane, okay, has a dip of 70 and it's facing towards 150. If this is north, we have a dip of 70 and it's facing towards 150. So indeed, these two information is giving me dip and dip direction, right? I can write here dip and dip direction, which is 70 and 150. If you want to convert this one to strike and dip, indeed the strike it's 90 degrees less than dip direction always. And if you want to actually take it into right hand rule, so the strike then it's going to be 0.60 and the dip is 70. Okay, this is a railway cut. And then the bedding attitude, let's say this is the cut, and the bedding indeed is 10. Okay, that's the strike, and it's dipping 50 degrees for southeast, and the friction, okay, is 30 degrees. So let me bring my Stereonet. I'm gonna work this one out with you. Okay, first of all, we can actually look at this problem by putting the poles of all the elements that we have on the Stereonet, or we can actually work directly with this planar feature. But since we are going to evaluate all the possibilities, it's better we work with the poles. I'm gonna start with the poles first, and then I can show you how we can work directly with the planar features right away. Okay, so let me put this one here. First, I'm going to plot my railway cut. So here it's north, and the strike was 60, 10, 20, 30, 50, 60, and it's dipping towards indeed southeast 70 degrees, right? So here I might actually put this one SE, which makes more sense, and you see the direction is towards southeast. Okay, 150, or we can go with this strike. You place that one here. I'm going to count from this direction, right? 70 degrees. Okay, this is my plane, and after drawing your plane, it's better you turn back to this original stage and make sure that the plane that you placed it's correct. So it's dipping 70 degrees, the dip is 70 and it's dipping towards 150. So you see this one's dipping towards 150, right, which is here it's south, here it's east, and the dip is 90 degrees. Okay, great. So here we should discuss about the daylighting term. Let's say I have the plane like that, which is 70 degrees, right? So do you think if I have a plane with, let's say, with 20 degrees, do I see the trace of this 20 degrees plane on the railway cut? Yes, of course, right? Because this is 20 and it's gonna cut this through. But if my plane that I'm giving as an example, it was 90 degrees, there is no reason, or there is no possibility this one will actually daylight on the surface, right? So whatever I have, okay, in general, if I have any plane with a degree of 0 of dip up to 69 degrees, even 70 degrees, it's gonna daylight on the railway cut, right? But if my plane has an angle of 71 to 90 degrees, so there is no possibility to daylight at the railway cut. Okay, so by knowing this, let's say I'm going to take this one into consideration. And also, my second question is, do you think the failure always it's gonna occur perpendicular to the cut? Yes or no? Of course not, right? Because the failure can happen in this direction, can happen in that direction, right? It can happen in that direction. There's no guarantee always the failure it's gonna occur perpendicular to the road cut or railway cut in this example. So if I'm going to show you the possibility of the failure, okay, if the failure may occur in that direction, maybe here, right, maybe in that direction, maybe here, and so on, right? There is a possibility of failure in different directions. So by knowing this, I'm going to use the pole of the possible failures to draw the unstable zone, right, which we say daylight zone. So let's say my first failure is perpendicular to that, the first possibility, the failure is perpendicular to that, and I know if the angle it was possible failure angle, if it was 0 to 70, it's gonna daylight, and larger than 70 it's not gonna daylight, right? So let's assume I have a plane with a 5 degrees or 10 degrees or 15 degrees, right? All it's gonna daylight. So what if I plot the pole of this plane, which is this one here, right? And I know any kind of plane that has a smaller angle than this, it's gonna daylight, so they will be unstable, and their poles it's gonna be plotted between these dot and center, right? Here it's 70 degrees, here it's 60, 50 degrees, 40 degrees, and so on to 0 degrees, right? These area can, or let's say the distance between this point and central point, these can be possibility of the daylighting of any kind of planar feature that has an angle less than 70 degrees. So I would put unstable here and stable here, because if I have a plane with 80 degrees, right, it's not gonna daylight, and the pole of this 80, it's gonna end up somewhere here, and it is stable. That's why I put stable. This is one. Second, we know, as we said, there is no guarantee always the failure is gonna happen in that direction, might happen in that direction, might happen in the other direction, right? So what I'm gonna do, I'm gonna rotate my vellum paper each time by 20 degrees in both directions, and I'm gonna actually find out where is the stable and unstable zone for that possibility. I'm gonna rotate this 20 degrees, and now I'm gonna, you see the intersection here which says 10, 20, 22 degrees, right? So if the failure happens in that direction now, the pole of that, it's going to be 90 degrees off from this intersection, the intersection of the arc and east-west line. So here it's 22. Either you can count 90 degrees from this towards that direction, or you can actually say 22 degrees from primitive circle to towards the center, right? I'm gonna show with this sign. I'm gonna rotate another 20. Now you see this is going to 25. So I'm gonna count 25 here and make a sign, another 20. Now it's 10, 20, 30, 38, 10, 20, 30, 38, right? And then another 20. So somewhere here. Now I have 10, 20, 30, 40, 50, 60, 67, 10, 20, 30, 40, 50, 60, 67. Okay, you see? And then the next one, it's going to be here, which is going to end up to the center, right? So let's see what we have done so far. So now I made a kind of, you can connect these points together like that, right? And indeed, whatever I have inside is unstable and outside is stable. So this time, I'm going to rotate the other way around with 20 degrees. So here I have 22. I'm going to assign 22. Another 20 more. This is going to be 26. Some here. And another 20. 10, 20, 30, 36. 10, 20, 30, 36. Another 20, which is now 10, 20, 30, 40, 50, 60, 64, 10, 20, 30, 40, 50, 60, 64, and again here. So what I can do, I should connect these points together, right? And indeed, the inside is unstable. What that means, it means the pole of any movement plane, okay, in any direction, okay, which gonna daylight, and the slope or the dip is changing from 0 to 70, okay, the pole of those all possibilities, it's gonna end up to this circle. So whatever we have inside, it's unstable, and outside is a stable zone. This is step 1. Step 2, indeed, I'm going to work with the friction, so I should take the friction into account. I know what it says. It says if you have two pieces on top of each other, and then let's say like that at a 0 angle, these are stable. If you increase this angle to 10, 20, 29, it's still stable. As soon as it reaches to 30, this is gonna fail, right? If it's like 45, it's gonna fail. If it's 80, it's gonna fail, right? So I'm gonna plot that plane, which is 30 degrees. And I know I'm working with the poles. That's why I'm gonna plot the pole. And it doesn't matter in which direction you're gonna start, because these friction angle or friction plane can be in different direction in space, right? You should take all possibilities into account. So I know, let's say if my friction plane or failure plane, it was at an angle of 30, you should count from primitive circle to the center, right? You say 10, 20, 30, and you could draw the plane. Since I'm going to work with the pole, indeed, I will count from the center towards the primitive circle. So about 30 degrees, I can place it here. And then what you need to do, if you have a compass, you can actually put the compass here and draw a circle. But right now I don't have it. What I can do, I will rotate, a little bit of this and still, sine this 30 degrees, right? You can do like that. And what's gonna end up, okay, it's gonna be a circle over there. I do this. Okay, great. So the dashed line indeed is the pole, okay, of the friction angle. So if we know this is the pole, and if the pole is between, you know, the center and this circle, which means the plane or friction plane is dipping less than 30. So in that case, inside of this, it's gonna be stable, right? It's gonna be stable here, and unstable everywhere, right? Unstable here, unstable here, unstable here. So, so now you need to find a zone that is unstable for both, right? So we know this is the stable zone for the friction, and whatever is outside is unstable. And for the railway cut, we know everything here it's unstable and outside is stable. If you look at closely, you will see this zone, okay, it's unstable for both, right? So in that case, you can, you can either, color it with another, pencil or so. Then you know this is your unstable zone by taking into account two different things, right? So now I want to know that the question is asking, if I have this bedding present in the area, do we gonna have a failure on that? Yes or no? So what you need to do, you need to plot the pole of this plane. If the pole of the plane, it ends up to the colored zone, which is unstable zone for both parameters, then of course you're gonna have a failure on that plane. If no, if the pole of that plane ends up to somewhere else, then it's gonna be stable. So let's plot that one too. It says that the strike is 10 degrees. Okay, the strike is 10 degrees and it's dipping 50 degrees towards southeast. So I'll place this one here. I plot with another color. And this bedding, it's 50 degrees towards southeast. Now I'm in southeast and I count 50, 10, 20, 30, 40, 50. Right, I'm gonna take that one. 50 degrees, 10, 20, 30, 40, 50. And the pole of this, either you count 90 degrees or you count 50 degrees from the center. 10, 20, 30, 40, and 50. And this is the pole of the bedding. And you see it's ending up to the unstable zone. In that case, this is gonna fail, okay? This is gonna fail. So this was, one way of doing it. The other way indeed is using the planes itself. So what I'm gonna do, I'm gonna erase this and solve it again with the planes this time, not with the poles. Okay, first of all, I'm gonna plot the railway cut. It was the dip direction was 150. Now I'm going to use dip direction to plot it, and the dip is 70. So if the dip direction is 150, you count 150 because it's failing. It's facing towards 150. 90, 10, 110, 120, 130, 140. And 150. All right, it's dipping that direction. How much? 70 degrees. So you bring that one to the east-west line, you count 70 and you plot the plane. Okay, so this is my railway cut, and as we said, now any plane which is dipping less than 70, it's gonna daylight on the railway cut, right? So in that case, here this side of the plane it's gonna be unstable, and the other side it's gonna be stable, right? So this is one, and now we're gonna plot the friction. So friction is 30 degrees, and this time, as you know, I'm going to plot the plane, right? So in that case, I should count from primitive circle 30 degrees, 10, 20, 30, right? So this can be a plane, but I know that plane is gonna be in any direction, right? So in this case, I'm gonna do the same as did before, right? You just rotate and you sign for 30 degrees, this time from primitive circle, because we are plotting the plane. Let me finish this first. Or if you have, compass, which would be easier and cleaner, you can actually open up the compass, arms, and just draw a circle with the size of, this circle. Okay, so now what we know about the friction, if the plane is between 0 and 30 degrees, okay, let's say this plane, if between 0 and 30 degrees, there is no, because the friction is big, okay, the friction is large, it's not gonna fail. If the angle goes beyond 30, like 35 and 40, this is gonna unstable and it's gonna fail, right? So in that case, I would say all the area less than 30 degrees is stable, and inside of this circle is unstable, right? So we know now, if we go back to our plane like that, we knew everything in that zone is unstable, right? Unstable. So if I'm gonna color the unstable zone for both, indeed it will be somewhere here, right? So this zone, it's unstable for both friction and the railway cut, okay? So what I should do now, I'm gonna plot the bedding plane, because the failure may happen on the bedding plane, right? And you see it's 10 degrees strike. I plot that one. 10 degrees strike, and it's dipping 50 degrees towards southeast. Maybe I use another color for that. And 50, 10, 20, 30, 40, and 50. Right? Okay, great. So I have this plane. So now it needs a little bit of, thinking. So if this is my plane, okay, and it's gonna fail, for sure it's gonna be planar failure, right? And and the direction of the movement, it's gonna be, it's gonna be like that. This plane, it's gonna move. If it moves, it's gonna move like that, right? So since this point, okay, or the arrow now is sitting inside of this zone, unstable zone, right? In that case, this is gonna be unstable. So whichever you feel comfortable for you, you can go ahead and do that one. But I feel plotting the poles, it might be a little bit tricky, but you're gonna end up to interpret easier, because rather than plotting a plane and thinking, okay, if this plane is gonna fail in that direction and this is the failure direction, now this point is sitting inside of this unstable zone, that might be a little bit tricky. But if you could solve this problem using the poles, you could actually plot the pole of the plane, and if that point sits on the unstable zone for both of the elements, then you can say this is unstable. Okay, thank you.